This presentation describes a popular use of one of the advanced design modules in Syndifluent, the solver. The solver is a general-purpose optimization module, but as I'll show you in this video, one of its most important uses is adjusting the unknowns or uncertainties in a model in order to better fit available test data. That turns out to be an optimization problem, to minimize the difference between tests and predictions. If you haven't watched the video introducing optimization yet, please stop now and go watch that one first. Just to set the mood, I'd like to start with a quote. To paraphrase this quote, all models are just approximations of reality, so we have to be careful about trusting them. Take that to its logical extreme just to make a point, and you arrive at the conclusion that you actually can't trust any of them. That's more than a little disturbing and probably not something you'd expect to hear from someone who works from a simulation software company. But of course that idea has to be tempered by finishing the quote. Again, to paraphrase the sentiment of the second part of the quote, as long as you're careful, a model is better than not modeling at all. In the context of this video, by careful I mean making sure that the model has some grounding in reality such that you can better trust any predictions it makes. Adjusting a model to better fit test data, or to fit even more elaborate component-level analyses like CFD data, is called calibration in some industries and correlation in others. I'll use the term calibration in this video. But either way, the idea is the same. We're dominated by pre-test uncertainties in the thermal fluid world. You can read the list here, but my guess is that one or more will resonate with you. Almost everyone is familiar with uncertainties in contact conductances, for example. Even if you know the materials, the surface finishes, the bolting patterns, torques, and so forth, you still can't estimate contact conductance ahead of time by more than, say, 20–30%. If that were the end of the story, it would probably also be the end of thermal analysis, since things like contact conductance are often in the critical heat flow path for something we're trying to keep from getting too hot or too cold. But if we were to take one measurement of the as-built contact conductance, that 20 or 30% collapses to a much smaller number, and not just for the conditions of that measurement, but for nearly all other conditions. So now we can trust the resulting calibrated thermal model when it extrapolates to many other scenarios, most of which we can't afford to test. So model calibration is absolutely critical for thermal fluid models. In fact, you could easily argue that thermal fluid modeling is not really useful at all without calibrating, at least not for finalizing a design. As an aside, dealing with uncertainties before test data is available is the realm of the reliability engineering module. And if you have to build many bolted joints but could only test a few of them, statistical techniques, worst-case bracketing, design margins, and all that still have important roles. But test data from a previous generation design or similar designs, or even more detailed analyses, are all critical steps towards trusting the extrapolations that your thermal fluid model is producing. Sadly, this critical step of calibrating your model can also be arduous. Too often, it's also informal. You have to be able to trust your calibration methods before you can trust a model calibrated using those methods. So for all these reasons, mentioning the phrase model calibration or model correlation to a thermal fluid analyst is likely to cause a bad reaction. There's a lot of scar tissue there. This is not a good situation, to have something that's critical also be something that people hate to do. Hopefully you'll despise this task a little less once you learn how it can be formalized and automated, but it's always going to be critical. Since the need to ground a model with test data will always be important, we can move on to talking about how to make it easier and more successful. Let me start by warning that the scope of this presentation is limited. I'll show you the basics, but it will be worth your time to explore the options that are available. After all, the need for model calibration will probably never go away. If you're watching this because you have an immediate need to calibrate a model, it probably isn't the first time that you've done that task, and you can probably be sure that it won't be the last. So it would be well worth your time to learn as much as you can about the tools and options available. And in order to keep this video from being too long, I'm not going to teach how to use the solver itself. That's a prerequisite which is covered in other videos and documentation. And speaking of other videos and documentation, I need to emphasize that a separate advanced module for stochastic design should be investigated as a companion to model calibration. Some uncertainties just can't be correlated away, such as variations in the environment or the probabilistic nature of manufacturing tolerances. And sometimes you need to deal with uncertainties before enough tests have been performed to narrow them down, so you need to design defensively. So I'd encourage you to investigate those features since they're actually fairly easy to use and learn, yet too often they're underutilized due to the lack of familiarity with statistical design methods. Maybe it surprised you to hear that learning how to use the solver, which is a general-purpose optimization tool, is a prerequisite to learning how to do model calibration. After all, a typical use of the solver is finding out what design gives the maximum performance or the minimum mass. But remember that the solver really has no idea what's going on inside the SyndiFluent thermal model. And we can exploit that fact. We can leave the design fixed and find the best model of that design. Don't adjust dimensions, in other words, adjust uncertainties in those dimensions. And more specifically, reduce those uncertainties by exploiting the availability of test data. Realistically, of course, you're less likely to be worried about uncertainties in dimensions as you are uncertainties in modeling parameters like natural convection, heat transfer coefficients, or as-built thermal resistance of insulation. Remember how calibrating a model has traditionally not been a popular task for thermal fluid engineers? Well, the bad news is that it isn't completely automated. You still have to ponder what is uncertain and by how much before making a comparison, and how to quantify it. In other words, you still have some of the responsibility for the resulting model. The good news is that it also hasn't been completely automated because you retain full control, yet most of the laborious tasks have been automated. When we pose a calibration problem to the solver, we still have to follow many of the same steps as we do when setting up any optimization problem. The first of these is to define what's uncertain, the correlation parameters or the calibration parameters. I can actually use whatever name I'd like here because the software itself still calls them design variables. I just have to remember that I'm not actually designing or sizing right now, I'm calibrating or correlating, so I'll call them calibration parameters in this video. Choosing what is unknown and what the range of its uncertainty is probably the most important part of a model calibration task. What if you pick something that doesn't matter? What if you forget something that did matter? What if you pick the right parameter, but you don't give it enough range? All of these are valid concerns, and to some extent you're always going to have to experiment at least a little to find the right answers. But don't let worry over these questions stop you from proceeding, because there are tools and techniques available to help, even if I can't cover them all completely in this abbreviated format. You also shouldn't worry about a model that was never built with calibration tasks in mind, because it's fairly easy to retrofit such a model with scaling factors that are initialized to 1. Then you can use those scaling factors as calibration parameters. When calibrating, the objective is no longer the efficiency to be maximized or the heater power to be minimized. It's almost always the error to be minimized. In other words, we want to move the uncertain parameters around until there's a minimum difference between model predictions and test data. Still, you can define this error in many ways. For example, it might be a least squared method. Even then, you might want to add weighting factors to make some of the points in time or space more important than others. And just so you don't think that least squared or RMS or RSS is the only method, I'll mention one other, the minimax method. In this one, the solver locates the worst comparison point and then tries to minimize the error just at that point. As you might guess, it usually ends up trapping the final answer between two such problematic points, where a slight adjustment in any one parameter makes one point worse and the other better. The minimax method doesn't work well with noisy data, since the noisiest point gets all the attention. So it has limited usefulness despite being popular in some industries. Mostly, though, we teach and document it just so you don't fall into the trap of thinking that least squares and RMS are the only ways to proceed. Finally, you need to produce a list of points to be compared with, whether by least squared or minimax or your own custom objective. For example, you may just compare 10 measurements at the end of a steady state or transient run for a total of 10 comparison points, or you might compare each of those 10 measurements every minute during an hour-long transient for a total of 600 comparison points. This comparison might require that the thermal desktop dynamic mode is on as part of the model evaluation procedure, depending on your choice of calibration parameters. For example, if an infrared emissivity is uncertain, you'll need to have RadCAD updating the model predictions during the SyndiFluent solver run. I'll talk you through a simple example. In fact, this example is derived from the same problem used in the solver introductory video, a fin or extended heat transfer surface. But this time, instead of adjusting dimensions to get the lightest weight fin, let's leave the dimensions fixed. This time, we're admitting that we really don't know the convection or film coefficient between the fin and the environment. To narrow it down, we've run 3 tests using 3 different power settings for the heater at the fin's base. We then measure the temperature of the fin at one point during each of those tests. Next, we run the TD SyndiModel of that fin at each of those 3 heater settings to predict the temperature at that point, and this yields our objective, to minimize the difference between the test and predictions for those 3 tests and 3 simulations. As you can see, we're using the square root of the sum of squares. We could just minimize the sum of squares itself, but taking the square root serves 2 important purposes. First, it makes the objective, the error, have units of temperature instead of temperature squared. Second, it keeps the magnitude of the objective from being too mathematically volatile, and that keeps the solver from getting confused or distracted by a poor initial guess of the values of the uncertainties. The whole point of performing this model calibration activity is to try to make a best guess as the heat transfer coefficient, so that becomes the quote-unquote design variable. Let's call it hconv, a single register, meaning that we're going to assume that a single heat transfer coefficient is good enough to apply to all the fin temperatures for all the locations on the fin. We could develop a more elaborate multi-parameter convection correlation that varied the heat transfer as a function of temperature and location on the fin, but I wouldn't do so unless I had a lot more test data than 3 points. Are there any constraints? Not in this case, other than perhaps limits on hconv, and that's not unusual in fact for calibration tasks, which means there might be room for multiple equally valid answers. To foreshadow a bit, that means we'll have need for pre-scanning when using the solver for these types of tasks. And finally, there's the evaluation procedure, where we evaluate the current model. In this case, we find the error resulting from the current value of hconv that the solver would like evaluated. In this verbal example, that takes 3 steps. First, we run 3 steady states, each predicting the 3 temperatures needed for each of the 3 heater power levels. After each run, we sum the square of the error term into object, or at least we save away the needed temperature values from each of those runs so that the sum can be done at once after all 3 runs have been completed. And finally, we take the square root of the object as a way of telling the solver how the value of hconv fared in its search for a value that minimizes the objective. I'm going to show you some thermal desktop features that help automate the comparison of test data and predictions soon. But there are also some SyndiFluent routines that help with those common tasks. These routines would be useful if you're using Synapse instead of TD, or if you're working with data other than temperatures, such as pressures or fluxes. I'll let you read up on these routines in the SyndiFluent manual if you think they'll be relevant, so for now I'll just list them quickly. The key routine is the compare routine, which can be used to perform various mathematical comparisons on 2 lists of values, one for test data and another for predictions. It has a side use too. It can be used to create a tabular report of the final calibrated model's performance. To get these values ready for the compare routine, there are routines like PrepList, which help collect temperatures, pressures, flow rates, and other predictions from the model. There are also other routines for extracting and interpolating test or CFD data, such as PrepDat1 and 2. These prepare the data into a format that can be directly compared with the predictions using the compare routine. Let's walk through another, more elaborate example, a thick aluminum plate that was used as an ammonia condenser. The plate is initially cold at 6.6 C. At time 0, saturated ammonia vapor at 29 C enters one end of the tube, at a flow rate corresponding to 500 watts worth of vaporization. As the ammonia condenses, it deposits energy onto the plate, and as a result, the plate warms up, since it has a weak environmental cold bias, until finally the vapor reaches the end of the plate almost 45 minutes later. We have temperature data at 3 points along this condenser, and we've made a thermal fluid model of the plate. But we could only guess at the bond between the plate and the cold environment since it was a commercial conductive pad. We also don't know how well we can predict the condensation coefficient, since this was actually not plain tubing but a grooved aluminum extrusion. We're not even sure that all the 500 watts that were applied made it into the condenser, or that the 29 C saturation measurement is actually correct. So I'll assign 4 variables as uncertainties listed here. The exact values and parameters aren't important to understand, and they're fully documented in the sample problem appendix of the SyndiFluent manual in case you want more information. Notice I take a stab at the upper and lower limits of each uncertainty. What if I didn't give them enough leeway? Well, if that were true, then the solver might return an answer that hits one of those limits, and in that case I'd have to decide whether to give it a broader range, or the fact that it hit such a generous limit might instead be an indication that something else was wrong in the model or the setup. When I call the solver, all the calibration parameters will be free to change simultaneously. I will use the least squared sum method, but I'll sum over all the comparison points, 3 points every 2 minutes for 42 minutes, for a total of 63 equally weighted comparisons per transient. And here are the typical results. You'll see the input power was about right. Maybe a little heat leak happened, but the uncertainty in the measurement was small. The saturation temperature was off by at least a degree. The incoming ammonia vapor was a little warmer than expected, so it was probably just measured at the outside of a tube and not within the fluid itself. The conduction of the pad underneath the thick plate was overestimated, but that's not surprising since only vendor data was available before the test, and they don't sell a lot of pads if they underestimate their performance. Finally, the heat transfer coefficient for condensation wasn't too far off. However, what you're not seeing is that this return value differed a lot between runs, with different variations such as solver methods or comparison methods, yet the other results didn't vary all that much. Why was this value so volatile? Because the value of this parameter didn't matter. It causes a very small temperature drop along the main heat transfer rejection path. In other words, it never should have been a calibration parameter in the first place, and it would have been weeded out had we done a little pre-scanning with dscan LH or sol check. Having failed to weed it out, we just wasted a little effort, but we didn't compromise the final results. Here's what happened. The black lines represent the test data, and the dashed red lines represent the initial predictions. After calibration is complete, the results look like this. As you can see, we've snapped onto the first two temperature lines, with some residual air at the end of the condenser as vapor is approaching that point. It isn't clear why that last line is not lining up like the first two. Maybe the thermocouple data or location is untrustworthy there, but it's more likely that something is missing from the model, such as non-uniform bonding of the interface pad conductance, or not enough credit was taken for portions of the condenser that cantilevered off the ends of the aluminum plate, or maybe some other uncertainty that was important but wasn't included in this first pass. As you can tell, the drudge work might be automated, but engineering judgment and experience are still important. I've alluded to pre-scanning, and that was covered in the prerequisite solver video, so let me just refresh your memory of it here. dscan LH can be used to search for a good starting point for the solver, and it makes a nice companion to the solver in general, but it's especially important for calibration tasks, since those problems are usually unconstrained, and they can also have multiple equivalent answers, which are hard to find if you don't first take a sampling approach. Pre-scanning can't work, however, unless all variables can be assigned both upper and lower limits, but that's usually not a problem for calibration tasks. And finally, you can use sol check in preliminary runs to detect weak or unimportant calibration variables and get rid of them. Since calibrating a model to test data is a common task, Thermal Desktop offers two modules that help automate the process. I'm going to just list them here, but I'll go into more detail later. First, there is the Data Logger Compare, which is part of the Logic Manager. Each data logger reads a set of test data and generates the syntologic required to compare that data with predictions, whether for a steady state or over the course of a transient, or some combination of those. If there are more than one data logger active, they combine their calculations into a single objective for the solver. Second, there is the Measures feature, which is a general-purpose way to either model a thermocouple or thermistor, or just to extract the temperature of a given location independent of the model underneath. If you are modeling a thermocouple, you can assign it to be a thermal node and give it a capacitance and conductance to the attachment point. Otherwise, if you're just attaching a measure to a location in the model, it isn't an active thermal modeling object and it doesn't change the results in any way. Instead, it just extracts the desired temperature at that location based on the temperature of the objects near to it. A measure can be used to produce comparison points for the data logger, but it can also be used independently for other purposes that have nothing to do with calibration, such as modeling a sensor for a heater controller. I'm going to cover the Measures feature first. Measures allow you to fetch the temperature at a particular point in the model without having to create a special node at that point, and without having to worry about relocating that node if the underlying model changes. In the diagram at the right, for example, a 1D bar is divided into about 20 nodes and has 4 measurements attached to it. These points are independent of the resolution of the bar. They won't move if the bar is changed from 20 nodes to 10 or 30. The measures will automatically interpolate temperature for the nearest nodes they find based on the current resolution. They'll also adjust if you change from a finite difference method to a finite element method for modeling the bar. You can place measures on a surface one by one, or you can import a file of XYZ locations to create multiple measures at once. If there are multiple TD objects at the same measure point, or if the measure point is not exactly on the surface, then a tolerance is used. This tolerance increases progressively if it can't find a suitable object at a tighter tolerance. This progression is the same mechanism used by the structural load set mapping options in TD. You can narrow down the list of possible attachment objects by placing the right objects into an AutoCAD group and then directing the measure to connect only to objects within that group. Measurement points have 3 output modes. First, they can be used in a post-processing mode, where they will display the temperature at their current location as seen on the picture here. But if you need to get access to the temperature during a solution, which you do need to do in order for a measure to report its current temperature to the data logger as part of a comparison, then there are two choices. First, you could make a measurement point a thermal node. Then you can refer to it as you would any SINDA node in logic or expressions or in the table headings for the data logger input file. This choice can be seen in this region of the input form, which is activated by clicking this radio button. For the inputs on this particular form, you could refer to the temperature of the node in this measure as tc.t1. You can also see the options below for attaching the node to the rest of the thermal model as needed to model a specific thermocouple. If you don't want a node to be created, you can instead name a register to contain the resulting temperature, which will be updated during the run. This choice is made in this region of the form. You can also see the search and tolerance options at the bottom of this form, which I discussed in the last slide. This slide shows the edit form for a data logger compare object, which is accessed through the TD Logic Manager. A key input for this form is the identification of the file that contains the test data and that names comparison points such as registers or node IDs. I'll talk more about the format for that text file in the next slide. The pull-down menu on the lower right lets you choose the basis of comparison. The option shown here is essentially RSS or least squared, except that the comparisons are weighted by time, and this means the test data towards the end of the transient will carry more weight than the data at the beginning. If you'd like, you can also name a file that will contain output from the comparison, although the data logger will automatically generate a report in the standard output file using the SINDAfluent compare routine at the end of the run. Finally, there's a region here at the upper right for naming the output registers that the logger will produce. These are optional advanced features used in logic. For example, they allow you to turn the logger on and off within a run. That would be useful if you want to run a setup case like a steady state before starting the actual solver procedure, and you don't want the logger to start its comparison tally too soon. I won't be covering these features in this overview, but you can read about them in the TD manual. You can have multiple data loggers in any one model. For each data logger, you'll need to provide an input file that both names the comparison points in your model and which contains the test data that you want to match with. The file at the bottom left is for a single time, and that's all you'd need if you wanted to compare with a steady state analysis. This file contains the data for 3 values, including a node temperature, a lump temperature, and a path mass flow rate. The file at the right is a list of a single parameter to be compared over the course of a transient at multiple time slices. A single node's temperature will be the entire basis of comparison for this data logger, but you could have many such comparison points. These input files can get very big. The first row of the file identifies what parameters will be searched in the model results when generating a comparison. These parameters can be any SINDA processor variable that gets updated during a solution, like the one shown here, or it can be a register. Of course, the temperatures of a TD measure object can be listed here either as a node temperature or as a register. The second row contains the units that are used in the test data in case they differ from model units. The remaining row or rows contain the test data. The solver will adjust whatever uncertainties you have listed as calibration parameters until the model produces results that best fit the data that you provide in this table. For transient, it will also need to know the problem time for each row, and that's supplied in column 1. SINDA will automatically stop at each such point, independent of the time step and output interval considerations, in order to perform a comparison at that point. Remember that you may use several data loggers in each model, in each one pointing to a unique file, and each file itself might have unique time points. When using the comparison method, though, the results will be combined into a single object for each time through the evaluation procedure. You should also note that these tables don't have to be test data. They could also be predictions made by a more detailed analysis, including a CFD code, but maybe even a more detailed TD SINDA model. In other words, you can perform model correlation to help generate a simplified model from a more complex one. I'm going to open up Thermal Desktop and show you a model that's set up to use these features, but first I want to go over the generic steps needed to accomplish calibration of any model. These steps don't have to be executed in any particular order. You won't get far, of course, if the model has not been built parametrically using symbols and registers, at least for those parts of the model that are affected by the uncertainties that need to be reduced. Although it's optional, if you're comparing temperature data, you probably need to define some measurement points and identify them in ways that correspond to the header row in your data logger input files. You will also want to build one or more data logger compare objects. These will generate the objective function for the solver, the error that will be minimized. It's probably a good idea to create a new case set that will perform the calibration task in order to keep it separate from other tasks that this model will perform before and after it's been calibrated. As a minimum, this case set should include a call to the solver, which is placed in operations. You may also want a Latin hypercube prescan, as I've discussed a few slides back. If the basis of this comparison is a transient run, then you may have to take the extra step before these calls and save away initial conditions, maybe after running a steady state. On TD's Dynamic tab, you'll also set the design variables, which, as you'll remember, we're calling calibration parameters in this video. If any of these variables require radiation or other geometric calculations when they're changed, then you should check the Use Dynamic Cinda tab to have TD respond to Cinda during the optimization run. In the Solver Control tab, you'll define how the solver will operate. You'll almost be certainly minimizing the error or the difference between test and predictions. And you'll almost always be using one or more data logger to help calculate that error for you, which is indicated by clicking the radio button shown here. The comparison procedure might be as simple as a single steady state call, but if a transient is involved, you'll need to take 2 steps before invoking that transient for each evaluation step. First, you'll need to reset the send initial conditions, which brings them back from the earlier safe part call that we put in operations. And second, you'll need to reset each data logger's tally of the error so it can start from 0. Otherwise, it would carry over the error from the previous procedure. This is the TD model I'm going to use to demonstrate some of the concepts that I've been referring to in the video. This model is actually the same one used in the introduction to the optimization video, which you've already seen, so I won't go into too many details here, except this time we're not finding the smallest bar, we're leaving the dimensions set and pretending that we don't know what the density and conductivity of the bar are, but that we'd like to back out the best estimate values of those 2 properties from a set of test data that were taken over a 1,000-second heating transient. You remember that the bar started at 100K and was heated on the end here, and that we followed it as it heated up and cooled down a little bit, or at least formed a gradient within that bar. I have test data at this point here, this node number 2, and the test data is as shown in this plot, showing the temperature starting out at 100K and increasing as the heat is applied, but then gradually cooling off as the rest of the bar starts to reject some of that heat. So those are the points I want to try to match at that nodal temperature point. Now, having the test data line up perfectly with a node is pretty convenient for a demo, but not very realistic for a real problem. So I want to show you the measures feature, which I've talked about in the notes. A measure can be applied at any point along the model. Say I want to place it here at this point between 2 nodes. And up comes a form where I can specify a register to contain the temperature. In this case, I'm going to choose just a node, whatever submodel I want, whatever node I want. And there's my representation of a measure applied at that point. I can assign this temperature for the node at the end of the measure to a data logger compare object. So as that temperature comes out, it will be applied automatically to the data logger if I did not have a node at exactly the right place. Another use of the measure, which I'll show you here, is for post-processing. If I post-process this bar, you'll see that it is showing a blank because it's been placed. The model was run without the node present, but I can still update the measures, and you'll see that the measure object itself becomes the color of the objects around it. It's not really a thermal node. The thermal node on the end here has not been updated since it was not present when that run was made. But if it had been, it would also be blue, and I would also be able to link it with a data logger. If I had changed the resolution of that bar, of course, the measure point would stay at the same location and interpolate between different nodes. But since I am fortunate enough to have a node at exactly the right place, I won't use a measure in this model. Now let me show you the bar itself, how it was parameterized. If I edit it, you'll see under the concap page, this is, by the way, a simple finite difference brick, one-dimensional. If you look at the concap page, you'll see the density multiplier here is set to a unit 1. If I look underneath there, you'll see it's a symbol called density factor that just happens to be initialized to 1, and that gives me the handle I need within the solver and of course within the automated data calibration task to adjust the density of that bar on the fly. Same thing with the conductivity multiplier, a symbol called conductivity factor that I will be using to adjust the conductivity of the bar during the solver run. Let me look at the data logger I have set up for this task. I only have one logic object. It is a data logger compare, and in fact I only have one data logger compare. So let me look at that, and you'll see that it consists of the input file, test.tlc, and if I looked at the contents of that file, you can see them here, and just as a reminder, that corresponds to this plot of the data points versus time. So I've assigned node T2 to be driven towards those temperature points during the course of the transient. I'm doing that with a comparison method over here called the time-weighted root sum of square root of values, which is a RSS method, but the comparison points have been weighted by a function of time of the run, meaning that the initial points do not carry any weight and the final points carry a lot of weight. So that's a useful technique when the initial condition is basically known and there's no point in matching it. It's assigning more of the weighting function to the projected points during the course of the transient. And there's other options here, some of which I wouldn't recommend, such as sum of squared values, since it's missing that square root that I mentioned in the notes is fairly important. This is a useful tool, the RMS error, for returning the square rooted value of the error, which returns it to units of temperature. Another option that's available, but I would recommend being careful with, is the absolute value of the maximum error. In other words, that's the minimax error that I mentioned in the notes. And the rest of them I'll leave for you to discover. Another option is the variable prefix string, which is a way of generating registers that can be used in logic or to control the controller. So keep in mind for now this name bar_test, and I'll show you later how that's applied in the data logger. That's the setup for the data logger itself, and now I'm going to show you the case manager, what was set up to actually perform the run. In the case manager I have one case only, the model calibration task, which is fairly unusual, but this is a demo problem. Usually I would have other cases for pre and post calibration activities. Let me look at this calibration task, and you'll see under the Cinda tab that the operations block has been customized by that asterisk at the end. If I look at the calculations tab, the user block has been overridden. So going back to the tab and opening up operations, I can see that it's fairly Spartan. I only have two parts for operations. The first is to save away the initial conditions, and I'm using a key of mtest that will be used to unlock those initial conditions later. And then I'm calling the solver. So all I'm doing is saving away initial conditions for the transients that will be called iteratively during the procedure. Where is that procedure? If I go to the dynamic tab, you can see it here, and it's considerably more complex. There's a lot of comments in here that are intended to help you, but you can see that the workhorse is the transient call. Every procedure I'm going to run a transient, but because it's a transient, as I noted in the video notes, that you have to set the initial conditions back to 0, back to that 100K uniform bar temperature, 0 time, using this call to rest bar and using the mtest variable to unlock the same location that was saved away by the save part call in operations. I also need to reset the data logger to 0 for the start of each transient by calling for data logger number 1. I'm calling argument 0, which means reset it. So if this were the second or third transient, it would not be accumulating error into the data logger. It would be starting fresh every transient. I'm also making a call then to td_setDes, which sends the design variables, or as you'll remember, calibration parameters, those density and conductivity adjustment factors, back to TD to do the dynamic updates. So you can see right away I'll be using the TD dynamic mode here, commanding TD in this TD case call to update its calculations for node masses, conductivities, and so forth. Then run a transient, accumulate the error based on that, and report it to a file, which I'll show you in a minute. And as a reminder here on the dynamic form, I'm using the use dynamic mode because I am using symbols that are also registers and need to be updated during the course of the run. In other words, TD is running in somewhat of a slaved mode from Cinda, where the Cinda solver is commanding it to update its calculations during the course of the optimization. And also, as I mentioned in the optimization class, I am rejecting the final values that Cinda is going to come up with here. I want to have manual control over that, and I'm leaving this box checked in order to look over the results before accepting them. Had this been a final run, could have accepted them by checking that box. In the Design tab, you'll see my two variables here, my two calibration parameters or uncertainties of the conductivity factor and the density factor. If I open up and edit the conductivity factor, you'll see it ranging from a minimum value of half to a maximum value of 5. In other words, it could go as low as half of the initial conductivity to a value as much as 5. Good idea to apply whatever limits you can here to keep the solver from exploring things like negative or zero conductivities, or to keep it from exploring values on the order of tens of thousands. All of those might be considered feasible to the solver unless you constrained it and kept it away from any unreasonable values. Otherwise, fairly simple definition of the design variables or calibration parameters. I've shown you the procedure blocks. The only thing left to show you is the control block. This consists of two fairly simple operations for a calibration task. The first is to click the minimization button for the goal and to set the object from the data loggers. I have one data logger here, but I wanted to inherit the object or the RMS time-weighted error from the one data logger I've set up, and then that's all I have to do for the solver setup. When I make the run, I will be getting a table as shown here. You've seen this in the solver introduction class. It is the design variables, or in this case calibration parameters, conductivity factor and density factor, starting at 1 and with an initial error of about 0.6 degrees. And you can see the solver gradually exploring and testing different parameters. It takes about 75 different transients here to find the values that it likes best, with a resulting error of about 0.15 degrees and a final value of conductivity of about 2.15, a little over twice the initial conductivity and a little less than the initial density factor. If you look at the Cinda output file, you'll see the same information summarized at the end, the conductivity factor and density factor reported in that table. And you will also see in the register summary up above 3 new registers that were created by the data logger using that prefix bar test: count 1, error 1, and active 1, all meaning the count and error and active flag for data logger 1. I will leave you to explore what the uses of the count and the error variable are in the TD manual. The active flag here, it is an integer register, is one that I mentioned in the video. It's the one that you would set to be 1 or 0 if you wanted to turn on or off the activity of the data logger. So in other words, you could set it to 0 in logic or expressions to turn off the data logger, say if you wanted to do some preparatory calculations. Otherwise, the final results for the run are best summarized here. You can see that the original test data points are shown. You can also see that the shots that the solver made, the different transients with the different conductivity and density values that it attempted while trying to fit that value. So this is a plot of all 75 runs at once. Kind of gives you a little flavor of the flow of it, trying different values and gradually narrowing in on the parameters that best fit that data. And you can see approximately the final solution shown here as the thick lines, which represent the most shots which were taken towards the end of the run as it was fine-tuning its final answer. And that completes what I wanted to show you inside the TD demonstration case. I'd like to summarize what we've covered in this video. As you've seen, tools exist to automate the adjustment of a model to better fit any available test data or any data from other analyses. 2 such productivity tools are the TD Measures feature and the TD Data Logger Compare object. The drudgery of model calibration, or model correlation as you might call it, has been greatly reduced, but remember, you still have complete control over the process and still have responsibility for the results. You need to take care to identify what is unknown and by how much, and what sequence and type of data comparisons will get you those adjustments you're looking for. A model built knowing that optimization, statistics, and calibration tasks will be expected of it probably won't have a prohibitive runtime, but you can help out by focusing the effort. In other words, using all the test data at once to calibrate a lengthy list of uncertainties will be inefficient, so it's best to plan a little and separate the adjustments into smaller subsets. Calibration is critical. Calibration is not fun, though at least now you should be able to focus on the strategy instead of the details, but it still won't fix a bad model. In fact, you should be careful that the model does not have defects that are masked by the calibration. In other words, a model will look better after calibrations are finished, but that doesn't mean it's right. Stay skeptical and look for places where the match isn't good, and see if you can figure out why not. Hopefully, you have enough test data to exercise that model under enough conditions that the calibrated model can be trusted, because there's always a test you can't perform or can't afford to perform. Otherwise, we wouldn't be doing a thermal fluid model in the first place. Thanks for taking the time to listen.